we have a system of nonlinear equations. It's nonlinear because several of the terms in the problem are squared. Now, we could do this problem using the substitution method, but I think it would be easier to handle this one with the addition method. Now, why can we use the addition method? Because notice that there is no way that I can add the y squared and the y and make them cancel. They are not like terms. However, I have x squared in both equations, and therefore I can multiply one equation or the other by some constant so that when I add the equations together, the x squares will cancel. So, what I need to do then is I do have to multiply at least one of these equations by a -1, because positive x squared and positive x squared, if I add up now, they're just going to double up. So I'm going to multiply my second equation by -1. I'm going to leave my first equation alone. So my first equation will still be x squared plus y squared is equal to positive 25. But my second equation becomes negative x squared plus y is equal to negative 13. Again, notice when I add these equations, the x squares cancel. Y squared plus y, they're not like terms, but I can add them and say that it's just y squared plus y. On the right side, 25 plus negative 13 gives me 12. And I now have a simple linear quadratic equation in one variable. Again, how do we solve a quadratic equation in one variable? Well, we want all the terms on the left side and 0 on the right. And if I can't factor it, I might use the quadratic formula. However, the good news for this problem is that I can factor this expression pretty easily. Y plus 4 times y minus 3 is equal to 0. Two numbers multiply negative 12, add up to positive 1, positive 4, and negative 3. Now that I've factored my quadratic equation, I can set each factor equal to 0. Y plus 4 is equal to 0, and y minus 3 is equal to 0, and solve each of those. I have y is equal to negative 4, and y is equal to positive 3. Now, I have half of at least two sets of answers. Keep in mind, to have a solution of a system of equations in two variables, every answer has to have an x-coordinate and a y-coordinate. I only have y's. In order to get my x's, I need to take my answers and plug them back into one of these two equations. It technically doesn't matter which, but I'm going to go with my second equation. I think it'll be easier to work with. So if I take my negative 4 and plug it back into x squared minus y is equal to 13, I replace the y with a negative 4. Now be careful with your signs. It's the minus sign that is part of the equation and the negative sign that you're plugging in for the y term. Make sure you don't drop one of those, because in the end they are going to end up canceling each other out. So I now really have x squared plus 4 is equal to 13. Now again, this is another quadratic equation, but notice I don't have any x to the first. I only have x squared in numbers. So this is a problem I can do pretty easily with the square root principle. I can get my x squared by itself by subtracting 4 from both sides, and then get x squared is equal to 9. So x is equal to, according to our square root principle, plus or minus the square root of 9. And of course, the square root of 9 is 3. So I'm getting two answers for x, positive 3 and negative 3. Now here's the thing. I plugged in one value of y and got two different x's. So what I really have now is two separate answers. One of my answers is the ordered pair positive 3 with negative 4. And my other answer is negative 3 and negative 4. Now I'm still not done. I still have y equal 3. So if I go through the same idea, x squared minus y is equal to 13, and I plug in 3 for my y, I don't have the extra negative sign to worry about this time. And same thing, I'm going to solve for x squared first by adding 3 to both sides. I get x squared is equal to 16. And again, my square root principle says I get 2 answers, plus or minus the square root of 16. The square root of 16, of course, is 4. And very much like the last problem, or the last half of this problem, I have 2 separate answers here. I've got x is equal to positive 4, back with my original y is equal to positive 3, and then x is equal to negative 4, together with y is equal to 3. So we have solved this system of nonlinear equations, and we actually had 4 separate solutions, 4 ordered pairs, positive 3, negative 4, negative 3, negative 4, positive 4, positive 3, and negative 4, positive 3.